Okay, guys, welcome back. Now, we've had a little bit of a chat about work energy, and there are just a few things that we can tidy up. The one thing that I wanted to mention is that there are lots of ways of solving this problem, okay?
Yeah.
There's not just one correct answer. So make sure that if you've been taught another method, and as I said, there are lots of ways, it will be equally marked. It will be marked just as correct if you get to the same answer. But I think that this is the easiest way to do it.
Yeah.
Okay.
And I would trust you, John. I would.
Okay. I'm glad. For example, somebody said, I've added the forces and then multiplied by the distance, but I was going to mention, and Malaji was asking about all the formula. That's why it's quite difficult. Remember over there, I've added in I've added the two forces to give me the resultant force, but you could equally do it this way. And I'm not going to do all the working. You could say a W net is equal to the work done by friction plus the work done by the component of the force of gravity that is parallel. And then you simply substitute in to there, and you're going to say it's the force of friction times delta x times cos theta plus the force Fg parallel times delta x times cos theta. And it comes out to exactly the same thing. Now, as I said to you, there are other ways. Some people have even gone as far as saying, well, we don't want to just write that. What we'll do is we'll write the whole thing down and just learn it. I don't like that, because if you forget it, then you haven't shown the bits that the examiners can pick up part marks on. So somebody's written in and said, well, can't we just write this as m dot g times sine theta times delta x times cos theta? And remember here, these two thetas are not the same. This is the angle of inclination of the slope, and this is the angle between the forces. So make sure that if you're going to write it like that, this should be sine x and that should be sine theta, but they're not the same thetas. So that's why this formula is a little bit problematic.
Yeah.
Okay, so the examiners might actually dock you a mark if you do that, but if you work out that one separately, as we did, we worked out that separately by using that formula, and then we substituted it in, there isn't going to be a problem in the way that you do it. Okay, so recognize that there are lots of ways. Now, the one other question that somebody's written in, would it matter if, say, for example, the object was sliding down the slope? Well, yes, it would. If it was sliding down the slope, and this is the last thing I just wanted to mention, is if it was sliding down the slope, if this was the slope, then what are the forces going to be on it? Well, we're going to have the force of gravity, the component of gravity parallel to the slope downwards. But now look what's happening. What's going to always act against, if something is going down the slope, pulling it down the slope? What we know, the direction of motion is going to be down the slope. And what direction does frictional force always act in? Opposite to motion. So the frictional force will be in the opposite direction. So if we did this one here, cos theta, okay, the theta of cos theta here is going to be 0 because it's in the same direction, whereas this one, your theta here is going to be opposite in direction. It's going to be 180. Okay, guys, I wish I could spend lots more time. Lots of you are asking about past exam paper questions. Yeah. I'm sorry we haven't got the chance to do all of them, but I know that later, after the live show, we are doing a mechanics section, and I did do in that mechanics section past exam paper questions like the ones that you're asking for. So please don't go away, stay tuned, and make sure that you pick up those pre-recorded sessions as well.
And John, what this question, what paper was it in? Do you know?
Yeah, sure. It was from Musa, sent it in. It was the prelim paper from Mpumalanga.
Yeah.
Okay, and it was question 5 on that paper, and it's great that you've shared that question. I really appreciate it. Thank you so much.
Yeah, I think Musa actually asked who sent. Maybe it's a different one.
But different Musa.
Maybe he said, "Oh, well, what is this question paper?"
Okay, yeah.
And this is 2.
Okay. Right, shall we go on to the next big question? We went through all the Facebook questions before the show, and we found work energy was the big
Yeah.
concern. Okay, the other big concern was questions around waves and light.
Yes.
Okay,
Yeah.
so we're going to go to a waves light question now, and we're going to start. I didn't quite pick up all the people that were asking for it, but we're going to start with this question, which does come from the 2009 paper, and it was a particular question about Huygens principle. Huygens principle says the following. It says that if you've got a wavefront that we're used to seeing a wavefront, we can treat every point on a wavefront as a source of new wavelets. So that's Huygens principle. And you get it written like that, diagram drawn like that, then what you need to recognize is each of these points can now start to radiate out new waves. So this point is going to radiate out some new waves, and the sum of all these wavelets will form the new wavefront. So where you get constructive and destructive interference, the sum of all these wavelets will form the new wavefront at a new time. After a certain time, there will be a delta x. That position can be determined by the addition of all of these wavelets adding together. Constructively, you will get the new wavefront at that position. Now, it's quite complicated. It's a drawing technique. It was invented years ago when people were thinking that light behaved like a wave. We still know that light has wave properties, but remember, light has also got particle properties because of the photoelectric effect. The question that most people then said, well, can you use Huygens principle to explain diffraction of water waves in a ripple tank as they pass through a narrow opening in a barrier? So that's what I just want to quickly sketch, and we're going to go and say there's a barrier, there's the narrow barrier, and what we're going to say is here's the wavefront. And the wavefronts were moving fine up until that point. They were moving in straight lines. Now what happens when they get here? Well, we can treat every one of these points as a radiating source. What we're going to see when it moves through is there's going to be bending. Remember what diffraction is? There's going to be bending behind the barrier. The narrower it is, the more bending there's going to be. So you're going to get this spreading out. The reason for the spreading out is this point acts as a wavefront. It's going to produce over there. It's going to spread out over here. So it's going to push out over there. There's not going to be anything to cancel out this region. So because your barrier is blocking the waves over there. Okay, I hope the picture makes sense. Remember, you can write a few words and draw a picture to illustrate what you're meaning. Okay, the next question, we've had a lot of these questions, which is about calculating the distance to the first or second black band or dark band. So when we deal with light, now we're talking about bending behind a barrier. What happens is we get constructive and destructive interference. We get regions of light that are dark and light. And I want to just show it to you before we actually tackle the question, and then we'll just do the question and make sure that we've got it sorted. So look what it says over here. Well, look let's just go through the question. It says a single slit of unknown width is illuminated with a red light wavelength 650 nanometers. Remember, 650 nanometers is equal to 650 times 10 to the minus 9 meters. Change to SI units straight away. Calculate the width of the slit in which the first dark band will appear at 15 degrees. Okay, so I want to sketch the diagram of what's happening first of all, and then we'll go and solve the problem. Because I don't know whether you're going to be asked to find the slit width, or to find the distance, or to find the wavelength. You could be asked any of those. So let's go and see what's happening. If this is my setup, there's my aperture, the little slit width. We've got light shining through here. Over here, let's pretend that's a screen. What are we going to see on the screen? We're going to see directly in line with this point here, directly in line with that point in the middle of the aperture, we're going to see a really bright white or red region. Now, I haven't got a red pen, but I'll use the pink one. So we're going to see a bright pink band. And we're going to draw it big because it's going to be big and it's going to be bright. So we spread it out like that. Then what will happen, it will fade a little bit. You know, like a thing just fades out a little bit. And we'll get a little sloping area over there. So it's very bright in the middle, and then it fades out a little bit. And then we'll get a dark section, and then we'll get another bright region that won't be quite as big as the first one. And we'll get another one, and so on this side as well. This is known as your dark band. This is your dark band. And this is your bright band. This is your area of constructive interference. So this is your bright or red band. Okay. Now you get lots of them, of these bands, alternating in pattern. What's interesting, and I know there was a question on Facebook about it, asking about the difference between single slit and double slit, or even if there was a diffraction grating. The more slits you've got, the more interference there will be, the more evenly spread that interference will be. So with a double slit, you won't get so much of a big band and then smaller and smaller and smaller. They'll be more of equal, and they'll be spread equally out. This light that they use is often laser light, and it spreads out, so you get hundreds of these dotted around a room if you're using something that's got multiple layers in them or splits in them. Okay, now what formula are we going to use? There was one other question that I just want to mention here. Somebody asked, well, if I'm given the wavelength, can I calculate the frequency? Yes, you can. Remember that C is equal to F times lambda, where C is the speed of light. C is equal to 3 times 10 to the 8 meters per second. So if they gave you the frequency and you had to work out wavelength, you could use that to do it. What's the formula for this? Well, we're going to say sine theta is equal to the m lambda over a. Okay, now take a look at what information we've got. We've got 15 degrees, we've got the wavelength, and we know that it's the first dark band. The m stands for the number of the band. So we know m is 1. We've got the wavelength. We want to find a. We know that theta is 15 degrees. You've got all the information you need. We're going to go to a short break. Okay? Why don't you plug it into a calculator, see if you get the right answer. You can check your answer straight after the break. See you in a minute.